Good evening, everyone. Thanks for coming up. Today I'm going to talk about the U-boot development report uh, from the beginning to the 2019 latest version. Little bit about me. Basically, I'm an embedded Linux engineer. I ran a simple embedded Linux company in India where we work mostly on the firmware and Linux kernel. And apart from that, I have one of the key maintainer in the U-boot, where I work for the main U-boot since from last 5 years. And I maintain Allwinner and spy subsystems, and I have some work related to build systems like Buildroot and Yocto. Okay, coming to the agenda, the main intention of this talk is to cover all the topics that are done since from the beginning of U-boot to the latest version of 2019.07, and I will discuss all the background related to U-boot along with the key functions or features that are merged till the previous version of 2019.07, and at the end I will summarize the what we learned since from the beginning of the project. Let's get started. The project which was started in the early of 2002, the project itself called as a DOS U-boot. The DOS is a code name here. From the day one, the U-boot itself is an open source bootloader, mainly targeted about PowerPC and ARM. The main intention was the bootloader at the time was to boot the system in a minimal way, like in the general purpose embedded systems at the time. But nowadays it's become more accurate towards the PCs and servers. We have a logo, of course, that is been done by last year because of OSFC. Till last year we don't have an exact logo, but we developed with respect to the conference attendance. This is a typical summary till the latest version. We have almost 1876 developers. Start from the beginning from the project till the active members, and we have 162 employers all over the world which are trying to sponsor our work, and we have 1 million of code which is still available in all the programming languages which required for the U-boot. Since the vast subsystems of SOC and new drivers and driver model, we have almost approximately 50 maintainers, and we have a headquartered in Tomlini, and previously was developed and things. We released a U-boot in the last July, so we targeted the next release in the October. So these are the supporting platforms. Though the bootloader has started with PowerPC and ARM, nowadays it's typically supporting all the platforms, all the SOCs and the embedded boards or PCs and some of the servers like KVM and Applied Micro, all about the boards which are supported U-boot till now. And even the programming language which is used for bootloader is C or assembly, but we have plenty of other programming languages which are required for the tools, like creating a package or creating images. We have much more programming languages other than C in our code. So we use TCL in the J-Links PC, the FPGA, Kermit or something. These are the typical languages which are used in our U-boot. This is how our development process started basically. The initial version of the U-boots where we targeted the 2 or 3 releases based on the front, but we have some kind of a development issues where we need to minimize the releasing cycle so that the features can be available in the next release version. So that is where the development process has been changed between the releases. But at the end, we think that the development process cannot be fixed in a 2 release or 3 months cycle. That means it's a dynamic. The coming version could be in the 2 month cycle, but it cannot be the same as the 2 months in the next version, something like that. So the development process will change based on the features that are hit particular in the merge window, along with the fixes which are available on our house, something like that. So if you see in the 2007 and 2004, we have a development cycle of 3 months. But if you see the cases somewhere in 2018.09 to 11, it was 2 months. So now the development process is dynamic. So it can be possible to have 2 months as well as 3 months based on the based on the crowd that are coming on the mailing list. This is the typical code changes with respect to releases, and how many lines of code we added between the releases and how many lines of the code we removed from between the releases. These are the one of the development process where we migrated many of functional drivers to driver model, something like that. So this typical statistics will show us how the number of lines will be added between the releases. If open source project coming into picture, we can assume that we need to see who is contributing the code and who is sponsoring the code. So it is our it's any of the open source fundamentals. You can likely to see the who is contributing in the more in the with respect to the code. So these are the statistics which related to who is contributed by alone by the developer and who are the companies which are sponsoring our code. That means the top contributors which I have listed in the statistics is a top 25 contributors from the industry. When I say the open source project is developing in a rapid way, there are also possibilities that who is reporting the bugs. So even the bug reporters also has a key role where we releases the we release the source code between the releases. So based on the bug reports as well sometimes. So it is one of the good statistics to even report the bug or who is doing the more bugs or something. If the project is going in a rapid way, we assume that the usage of the project is based on the developers in the industry or what is the new companies which are using the U-Boot in their hardware prototypes. So in each and every release, we have some kind of a developers from the open source as well as companies, and we have some kind of employees which we gather between the release. So you can see that between the release, the release periods from 02 to 07 or any of the release period, we can assume that the number of employees who is sponsoring is 20 plus, and we can see 100 plus developers on our board. So these are mainly focusing, these are mainly focusing the project statistics, and I will quickly start the project, the key project developments which till now we had added in 2017.09 with respect to our development phases. The first feature will be K build. When I say U-Boot, initially the U-Boot comes with normal build systems, like we have a conventional makefile, so you can do some sort of makefile things. So the source code will build accordingly, and it will show the normal makefile syntax. But in 2014 and 2015 time, we come up with an idea by forking the K-build system from the Linux, and we build the U-Boot to completely to K-build systems. Like it uses the kbuild config, kbuild.conf, how we use it in Linux. So we reuse it in the same thing in U-Boot, and we finally merge it to the kbuild. This is one of the key features which have been merged in 2014, where and previous to that we don't have any kbuild. And next thing will be in the kconfig. Since it's a project driven starting from the ARM to PPC, so the config items which we listed does not have a particular pattern. So we created some normal files, and we defined those configs, and we maintain some board.config globally, and we define the code based on the if and else macros. But in 2015 we come up with kconfig. So we have a migration from all the board configs to respect to drivers or tools configs, something like what Linux does. So we finally merged all the kconfig. We finally merged the .config into fconfig files. So the board configs are any particular driver. Now we are using the kconfig items. These are the typical tools and testing builds which we have been developed since from the years. There was these tools which we likely to have an active project that would take our code into more actively maintained or more buildable toward the releases. So we have the tool which was in 2013, I guess, was a Pathman. It could be a pretty old, but the tool itself is showing some kind of a tooling where we can send patches to the mailing list in a big way. Like if you have a bunch of patches, you can use a git send email, right? So that this tool will take care of who is the maintainer for the particular subsystem and who want to send the patches, what is the mailing list idea or something. So this Pathman is some kind of a tooling to git send mail. And we have a build man where if you change something into the particular global source code, I wanted to build all the platform with respect to the particular change. We have a tool called buildman. So so the main maintainer or sub maintainers will usually do the buildman. So they think that the particular change is not affecting the other changes. So they come up with the solution so that they can move forward to pick the patches. And we have a Traversy build. This build was we have a traversy.aml file. So we listed out all the boards and configs which are related to U-boot. So once we have a Traversy build, there was a Traversy build system runs with all the platforms or affected platforms and boards. So that is how we replace the build man with Traversy in the 2015 releases or something. We have some Python test cases which are morely related to driver model. So if your new developer or employee come up with a new driver model or new device, so he can need to write some kind of a test in the sandbox. So those sandbox tests can be validated using test.py. We have a Traversy, something like in Linux, where you can see the function called trace between the driver model versus the command, or command versus some architecture code or something. These are the typical tools which we have been developed since from the years. And now I get into more U-boot area where how we developed, how we started the U-boot, and now what have been added between the releases, and and then finally where we are with respect to the firmware or any other stages or something. This is a typical U-boot. The thing where we started in 2002. Usually the bootstrap or bootrom code will call the bootloader that will launch the Linux kernel somewhere. So the U-boot sits at this particular area as a bootloader. So say for example IMX2 or IMX3, where we have IMX.mx, U-boot.mx. So we don't have any subsystems. So the bootrom will directly load the U-boot, and U-boot will load the Linux kernel, something like that. So as years going on, in 2014 or somewhere, the SOC vendors are coming with the first stage bootloader. Those bootloaders typically called as SOC loaders. Say for example, Xilinx says FSBL and Texas Instruments as the XLO or something. So those SOC loaders or first stage bootloader has not been part of U-boot at the time. So we have a communication where we need to pick all the code into U-boot, so that become the first stage bootloader. So that the code which is related to SOC loader can be some kind of a DDR scripts and some kind of a FPGA bit streams or something. So we finally make that SOC loader as an SPL. So this particular stage has been added so that the SOC vendors cannot keep their first stage bootloader into their proprietary area. Since the SPL runs in the SRAM, there are some use cases where the SRAM cannot fit the full bunch of SPL. So something like there are some cases like 8 KB SRAM or less than 8 KB or somewhere. So that is where we would come up with another stage of bootloader called TPL. So
can you explain why it's called the secondary frame loader? It's really confusing.
Yeah, that is one of the terms that even I confuse basically. The SPL is a secondary boot stage loader, assuming that the boot RAM is a first stage boot.
You have to count up, can't count backwards. Would have been in real trouble with naming TP.
Yeah, that is how the typical stages has been done with respect to the SRAM and DDR. And when it comes to ARM64 or 64-bit servers, there was trusted firmware. So we have trusted firmware stage. One more stage is coming to picture called TFK. So the bootrom will pick the SPL, and the SPL will in turn launch the TF. trusted firmware that will in turn launch the U-boot proper. So if you understand that when it comes to the third stage, U-boot becomes a U-boot proper. So typically we cannot call it as a U-boot. Since we have another stages called SPL and TPL, U-boot becomes U-boot proper at the time. So this is how the trusted firmware has been loaded in the ARM64. And we have one more stage of bootloader that require sometimes in trusted firmware area where that is called OPTI, the trusted OS. And U-boot is also been supported this trusted OS in the two different chains. For ARM v7, this OPTI will sit in SPL to OPTI, but in case of ARM64, there are two different. In ARM v7 we have two areas, like you can load the OPTI by after loading SPL, or you can load the OPTI before loading the Linux kernel. Something like that. These are two different use cases with respect to how I can load the trust zone on particular trusted firmware OS. This is the case with ARM64. Since ARM64 has ATF, so you have to have another stage called firmware with respect to OPTI. So you need to load OPTI first and then ATF, and then ATF load U-boot proper, something like that. This is the global the typical U-boot sequence where you can consider all the changes in together. So there are two different areas, two different sections in the booting sequence. One is before relocation and after relocation relocate code. We call it as _F and _R. So any system which start from the scratch is typically create a global descriptors that will ended up having to relocate themselves to a lower order higher memory area. So the respective stages will reload themselves, and finally it will launch the shell or it will load the Linux kernel. The next topic would be image boot, which is being more complex in between the releases. When we start, when we have initial project, we have a legacy image called normal Linux kernel. How we can load the Linux kernel with the Go command, where we ended up having some kind of issues with this legacy image based on the features been added, or based on the flexibility of the image loading, or even the integrity or security extension toward that image. So finally we moved in 2015 or somewhere with the fit pattern image tree, where we have organized all the images in the device tree format. So the U-boot is been supported all the images with respect to some kind of header, along with the header can be a kernel, or header can be some kind of DTB and rootfs. So you need to format, or you need to define the structure in the fit format. So U-boot can identify the fit and it will load according to the fit, how you organize the fit. This is a typical fit image in that we have considered in U-boot. If you see in the first section is the Linux kernel, and next section is the DTB, and we have this is how it will load during the loading process. It identify all the hashes with respect to particular section of the fit. So it finally lands the Linux kernel. And as features has been evolved, this fit becomes more complex. So initially we added only Linux kernel and DTB, but with the fit we can add multiple device trees and multiple kernels. This particular use case is coming up with respect to server areas, where if I wanted to boot the one of the Linux that has been crashed somewhere, or some particular issues, so you can update the DTB with the next DTB on the fit image. So you have a flexibility to load the different images and different kernel images at that time. So you can add multiple DTBs and RAM disks to that, and some kind of FPGAs like a JRing sync come up with bit streams. So you can add the bit stream to the fit as well. So it can be another kind of a header to that fit image, like Linux kernel and DTB, and even you can add ATF. So the idea of the fit is to pack everything into a particular section. So at the end it will create the output fit. That is a single image can be loaded during the process of loading. So there are we can even add the OPTI, And there are some other use cases also. If you want to have a new image type, you can also add the new image type to the fit, which is how it is more flexible. As I said, the fit has a complexity of adding more and more, and this is one of the software secure boot along with the fit. So I can create some kind of a keys in the software area using some kind of a algorithms, OpenSSL algorithm. So those keys can be reset in the U-boot device, and those can be verified during the boot process. This is something like a secure extension towards the fit. So you can have a secure image that can be part of the fit, though that can be verified during the U-boot loading. So the particular public key can be part of device key or somewhere. This is a typical software loading. But if you extend this software into hardware, there was one more section called FUs. Instead of having to pump the public key into device key, you can pump the public key into FUs. So the hardware, during the hardware boot ROM installation, it can grab the public key and it will verify the boot process. This is also one of the fit extendability, but this is into particular in the SOC specific. And this particular chart I have had taken it from, I have tried it from IMX6 app before. This is also next version of the secure extension called encryption. Okay, and there was a use case where one of the boot process has been slow sometimes, since we have multiple stages. So you can skip some of the stages in the bootloader so that you can load the Linux kernel or next particular image faster than what we have done exactly. So that is where this Falcon mode coming to picture. So you need to configure the Falcon where I need to load from my kernel image or nest application. So during the nest boot, the boot stage will skip the U-boot proper. It will directly boot the Linux kernel directly from SPL. That is how this name becomes a Falcon here. I did some kind of a measurement. These are three different applications I have come across with Falcon mode. I did a typical example on some kind of a ARM board where I boot the system with normal flow, and I will boot the system with Falcon mode. Approximately, I got 40% of boot rate because it depends mostly on how U-boot proper is taking or initializing your devices. The next stage is very much useful for the PC systems and particularly on the PCs or servers. And the systems ARM64 and x86 come up with UEFI. So in 2016 or somewhere we have added UEFI support to U-boot. So the UEFI boot is something like it can be a payload for the U-boot. So once the U-boot coming to picture, you can load the UEFI image. So the U-boot can understand even the UEFI image format as well. So this is so that you can even boot the Windows or you can boot the ARM64 UEFI systems or somewhere. Something like what you did in the grub. And we have a distro boot supports like how grub or other bootloaders are using the distros. Like you can load the Fedora or Ubuntu in the distro formats. So we have a distro support so that OS or distributions can be loaded from the U-boot itself. And have coming into the other section of U-boot development, where we started the device tree. Before to the 2013, we don't have any device tree like Linux does in the platform device. So all the devices we are using on the particular hardware, we need to categorize in the structure format like what we did in a Linux kernel platform device. So we started using the FTT as well. So this is typically same as like how Linux FTT does. And with respect to the Linux bindings, we have separate bindings on the U-boot. Those bindings are termed as U-boot minus DM prelock. These particular bindings are required from SPL stage. Since the SPL stage is very small, we don't need to use all the bindings which are required for the particular DTS. If you use that, it ended up in a different size. So if you construct that size, we have some kind of a property called UBDM PLC and UBDM SPL. This is how I've used one of the bus in the SPL stage. I've called it as a U-boot minus DM SPL. This particular AIPS U-boot will be initialized during the SPL stage. So I cannot consider all the nodes which are in the tree. Instead of going for the entire tree, I can go with particular property. So this will eventually reduce the size for the SPL. And there are some use cases in the U-boot. Before loading to the Linux, I need to update some property in the device tree. Say, for example, I have a MMC. I wanted to change the. I have already loaded the device tree, but I wanted to change the MMC one of the MMC properties. Say, for example, I want a bus width of 8 instead of 4. So that is where we have some kind of use cases. So there was a library called libftt, where you can change or update the device tree before going to the Linux kernel. So initially we used a libftt, but it ended up different drawbacks, because I need to traverse. If you see in the second in the code, I need to traverse all the device tree and to update the particular property of the node. So these are the typical. For this, we have some kind of issues for traversing, because the traversing becomes very slow. So I cannot directly go to the particular property and do some kind of a change. This is where we come up with a concept called live tree. So this is a kind of a pointer concept. So I can directly go to the particular section of the property and I can update instead of traversing each and every tree on the device tree. And we have in 2017 we have added the FDT overlay supports. So the FDT overlays can be added using the fit image, and even I can add it by manually if I wanted to have a different hat on my board. So I can download the DTB along with overlay. This is a fit image FDT example, overlay example, and this is how I can load the overlay during the commands. If you see in the overlay, I load the MMC base.DTB, that is a board DTB, and I will load overlay DTB as well. At the end, I can resize the FDT and I can load both DTB along with overlays. And as the driver model gone to the picture, there are some issues using the device tree in the SPL. So if I wanted to, I don't want to use device tree in the SPL. So we have a concept called a off-platform data. This is similar to platform device entry in the Linux. So the low SRAM boards which are using SPL can go with off-plat data instead of going for a full device tree. So I ended up with a next example of development, which has been started in 2013 called driver model. So till 2013 we have an issue with the drivers. Like if I wanted to access some kind of I2C, so I need to traverse to the I2C by directly calling the function calls. So it becomes more headache. So we cannot control the two different slaves in the particular same driver, because it ended up having multiple definitions of using the same function call. So in 2013, initially the project has been stalled in 2012 and restarted in 2013. We come up with a new approach called driver model. So the implementation of the driver model is something like you can compare the device mode in the Linux. Say for example, in the Linux, we have a bus tree and we have a devices and we have a classes and everything. But in case of U-boot, the driver model is homogeneous. So you cannot have multiple types on the particular hierarchy. All the hierarchy in the 3 stages. One is the device, and second one is the driver, and third one is the U class. If you can take any of the devices from U-boot point of view, the driver model is in fit into all the 3 stages. So this driver model we adapted and we have used it till since from 2013. So the new drivers which are coming to U-boot will end up using the driver model. There are some kind of advantages as well as some kind of disadvantages for this. The disadvantage can be a small size issues when I use in SPL. So we cannot take it because it's a driver model. So The driver hierarchy is having much examples rather than the drawbacks. The main advantage I can see with the driver model is the lazy initialization. If you see in the this is the U-boot after loading the driver model. If you see the pluses which are loaded during the U-boot, but if you see the clock and ETH and USB, there are not pluses. That means they are not being loaded yet. So this is a concept called lazy initialization. So since it's a bootloader, it's not a Linux, it's not a OS or something. I just wanted to load what are the required devices which are required from my U-boot boot process, and I don't want to load other devices at the time. I can load the next devices during my usage time. That is how we can skip most of the devices which are not required during boot time. And this is I'm giving you all the examples of how driver model looks like. This is a CPU drivers. Each driver has as I said, each driver has a U class. So U class is something like a core. So in case of CPU, it can be a CPU class. In case of RAM, it can be a RAM U class, something like that. If you have a watchdog, it can be a watchdog U class. And each platform data or device can be hardware or devices. And the controller driver and RISC-V and CPU is a controller CPU driver, and MSM is a controller driver, something like that. Even the power domains, we have a power U classes for all the regular regulators and the PMIC, even if the thermal and timer, and all the controller drivers sits in the driver area. And we have some kind of a core DMs, the pin controls and clock and pi. Each and everyone has individual U classes with respect to the controller clock drivers or controller Xenix. We have peripherals, SPI, I2C, Ethernet, SPI flash, everything. And each and every one has a U classes and with respect to controller drivers. And this is how the typical driver looks like in the U-boot. The upper one is a U class driver, that is a core, and the second one is a U driver, the U-boot driver, that is actually the controller driver. And this is how I can write some kind of operations to the U-boot driver. In this particular example, I am using a driver model of clock and reset in USB Pi. This is a generic block layer where we classified all the block devices in a particular U classes, and we have a U block core that will interact with the block layer commands. So the MMC, SHA, and SCSI, NVM, which are required for the block, are sits between the block to block layer. And this is a USB framework. This is some quite different with respect to the U classes, where we have handled both host and gadget. So host and gadget have separate U classes with respect to separate drivers. And we have some kind of a tools which are has been adopted since from the 2013 with respect to device firmware upgrades. So we have a fast boot and DFU tools. If anyone want to upgrade their images in the U-boot, we have these kind of facilities. And I have some kind of a miscellaneous features is been added since from the last two releases. And we have a debug. Earlier we used the printf, but we don't have some kind of a early debug. We have some now we have some early debug driver that will use for the debugging. And recently we have added the Android verified boot that is typically used for the Android devices where they wanted to use a Android verified boot process with AVB command. And in the last release, we some Intel has adapted the Slim boot. We also supported the Slim boot in the last release, and we have enough x86 development is going on with respect to Slim boot, as well as in some Apollo Lake bare metal codes in the x86 from Intel. As Simon said, that we have a binman, so where we can pack all the images together and we can pad them together, and at the end you can use a single tool, because we have enough stages like SPL, TPL, ITF, and U-boot Linux and RAM disk, right? You can create a package image so that it can be handled alone by loading a single image. And coming to the regression test, like a continuous integration, what we have in the Linux as a kernels here, we have a simple test tool called tboat. So you can run the continuous integration tests on time into the target using some kind of a scripts in the tboat. But this tool is still in the development board, and it requires more testing and new features. And yes, at the end, I am going to give us some few more information with respect to the project. These are the typical lessons we learned from the last 18 years. Though the project has been started with the ARM and PowerPC, we mostly have support for most of the platform and most of the architectures. And though though the project has been started only targeting on the embedded device, we have some kind of a development on PCs as well as servers as well. And now we have enough maintainers and there's enough key takers who are sponsoring and developing our work. And we have dynamic release cycles, which has been discussed since from between the release and since from the starting of the project. These are typical areas where development is going on. We still have to have some kind of a kconfig migration has been done, and we have driver model migrations. So this is something like we are some kind of a lag, but there are some subsystems like SPI which I was maintaining. Most of them have been converted to driver model, but there are some peripherals is still under migrating to their driver model code. And if anyone interested in any particular, so this is an easy way to collaborate with U-Boot. The new ports will always use the driver models with respect to DTs. So if anyone have any questions, we have an IRC and we have a mailing list as well. Thanks.